Hello, everyone, and welcome to this presentation. My name is Viali Kazadi Mutombo, and I'm going to present about energy balancing routing protocol based on reinforcement learning for wireless sensor networks. This is actually a paper which was accepted for publication in the 36 ACM Singapore Symposium on Applied Computing Conference. This is actually a virtual conference due to coronavirus. So starting with the outline, I would like to give the outline of this presentation. First, I'm going to talk about the introduction of this paper, and then I'll give an overview of reinforcement learning, and then I will talk about related work. And the fourth part will be actually the scope. Is actually the scope of this work, which is energy balancing routing protocol for, using reinforcement learning. Then will come performance evaluation, and finally conclusion and future work. Well, starting with the introduction, so I would like first to discuss a little bit about wireless sensor networks. So wireless sensor networks, as the name indicates, is actually a network of wireless sensors. So wireless sensors are inexpensive devices with sensing capabilities. They are used for various applications in order to monitor environments or track some objects. Initially, they were used in military application for tracking the battlefield, and later on they've been applied to different fields, and they actually used also in IoT. I would like also to indicate that a wireless sensor network is actually the backbone of IoT. So why people always talk about energy efficiency when it comes to routing protocol using in wireless sensor networks? The reason is that a wireless sensor has four main components. The first one is power units, which is actually a battery which supplies power to other components. So this battery, it's actually it's a low power battery. So the sensing unit, it has a sensor and a analog to digital converter. Actually, it senses data and then pass it to the processing unit, which also use a microcontroller or microprocessor to process the data and store them, and then pass them to the communication unit. The communication unit will then send the data through the network. However, these two units, sensing unit and processing unit, they consume really negligible energy. But communication unit is really the most consuming. And as I said, wireless sensor networks, they operate on batteries, and they actually deployed in harsh environments where it's really hard to replace or recharge the battery. So once it's dead, we need to replace the node. So this is really not good. This is not good. We need to extend the network lifetime. That's why people always mostly focus on energy efficiency before considering other parameters. So that's why actually before there was actually only flat-based topology, and clustering topology was also created in order to deal with to optimize also energy consumption. And the communication in wireless sensor networks can be done in two modes, either in single hop. That means this node here, which is far from the sync node, can communicate directly with the sync node, but this is actually very energy consuming, because it sends the packets really far. It consumes a lot of energy. So therefore, it needs multi-hop communication. That's why multi-hop communication is very used in wireless sensor network. So, and recently, reinforcement learning has been also used in order to deal with energy efficiency, because actually reinforcement learning allows nodes to adapt to any change about in the environment. The change can be either when the energy level changes a lot, the node will try to optimize the energy consumption. So reinforcement learning operates such that an agent try to act, try to perform an action in a unknown environment. Actually, initially the agent is in a certain state, let's say ST, and then it in this state it will perform an action AT from this environment, and then it will get back two things. The first thing it will get is the reward. The reward is actually the compensation for the action performed, if the action was good or bad. And then the state changes also. So the agent will change the state to ST1. The environment, sorry, will change the state to ST1. So this is how, and the agent will keep improving using the reward. So in this can be the same thing is applied in routing protocol for wireless sense networks, where a state set can be actually maybe available neighbors, and the action set can be available routing information, where a specific state or a specific action can be through the next hop, which node can be the next hop. The reward here can be getting back the receiver information about its like residual energy or location, to know whether the node is still there or whether the node can actually has enough energy for next time, and then it will update the Q value. So there's different research topics, or there are different actually various works, actually a lot of works that have been proposed before. Can list here some, like a Q routing, energy balancing in multi-hop wireless sensor network using reinforcement learning, or there is also energy and QoS routing based on reinforcement learning. There is also this FROMS, which is a feedback routing protocol on multi-sync. So all these works have their own advantages and drawbacks. So for more reference, please refer to the manuscript. So in this work, we're going to talk about, in this part actually, we're going to present the scope of this paper, which is energy balancing routing protocol using reinforcement learning. This protocol was also actually designed into two phases. The first one is the setup phase, and then the communication phase or data transmission phase. The setup phase here is actually the initial phase where the network need to be set up. So first we assume that each node knows its location and the base station location. And secondly, we don't assume, sorry. Each node will compute its initial Q value using the distance or the hop count. The hop count here is computed based on the distance link and the residual energy. Initially, the distance link can be computed is just the Euclidean distance between the node, and the sink or the base station. And later on, when the nodes will know through which neighbor to send the packet, it will compute the distance a little bit differently, but the difference will not be that big. But still, this will help to improve a little bit the system. To improve the energy consumption. So after that, each node will send a heartbeat message, a heartbeat packet to with its local information such as initial key value and location to its surrounding, and every node will also get information from the surrounding and save its routing table. So the protocol runs like this. The first step, first the nodes will try to find the neighbors, and then compute the Q value. Actually, this one can be omitted. This part can be omitted because, as I said, each node will already send the Q value, its initial Q value, and the nodes in the surrounding or the neighbors will sense that packet and extract the initial information of each node within its surrounding, within its neighborhood, and save it in its routing table. And then there will not be need for each node to compute the Q value for each surrounding node. So the third part is the most important here, is it consists of choosing the node with highest, I mean the strong node, which is the node with highest Q value. That's why we put here max Q. So every node will compute the node, will compute, will try to find which node has the maximum Q value in its environment, and it will compare it with its own Q value. If the it has, if the Q value, if it has only like if it is the strongest node, we'll see it in the second part of this algorithm. If it's the strongest node, then it won't need to choose any node as a neighbor, because as a next hop, because it will be the strongest, it will be chosen by other nodes. So the communication phase also is actually, this is where we applied the learning process. This is actually the learning process, where the learning process is applied. It consists of sending packets and then updating the Q value at each packet transmission to enhance energy efficiency. So for this purpose, we used three functions. The first one is energy consumption model. This model will help each node to update its residual energy, its remaining energy. What is the energy remaining after the packet is sent? And the second function here is it's a reward function, which is computed based on energy and distance or hop count. So here there are some probabilistic variable such as P, which is associated to energy, and 1 minus P, which I can also call as Q, which is associated to the hop count, which means that if P is bigger, that means we emphasize more on the energy, the residual energy. But if Q, 1 minus P, is bigger, that means we emphasize more on the difference between nodes. So these two parameters are used to compute the reward function. But if a node has less energy, then its reward will be 0, will be minus 100. If it has like if it has energy which is less or equal to 0, that means the node is dead. So its reward will be minus 100. And then this reward here, computed here, will be used to update the Q value for the long run, which is, this is like a long-term reward, if I can say it like that. So data transmission here, first, all the strong nodes or nodes within the communication with the sensor, with the cluster head, with the sync node or the base station in their communication range, do not need to send node through other nodes, do not need to send packets through other nodes. However, they can directly send packets. However, if they have been chosen as a next hop, then they can aggregate first data from other nodes and then pass them to the sync node. And or if they're not chosen, they can just pass the data to the sync node and compute the reward and update the Q value. For nodes which are not in the same range with the cluster head, or which are not like the strongest, they will also here do almost the same thing. First, they will check if they have been selected by another node as the next hop. They can aggregate the data and then send them to the strong node. They will first try to find which one is the strong node, and then if they have been used as also to aggregate some data, they can also send those data to the strong node, and the strong node will aggregate the data and pass them to the sync node. Or if they don't have any data to aggregate, they can just simply send the data to the strong node, and then update the compute the reward and update the Q value. So for implementation, we use these parameters here. So we deployed like 100 node in a 100 field, sensing field, and the sync node was placed in the middle with these values, initial values, and the alpha, which is the learning rate was 1, and the gamma, the distance factor here, was 0.95. And after running the initial routing algorithm, we got this result. So this is like the initial route. You can see the links. And then the second thing, we try to find the impact of probabilistic fast factors associated to energy and hop counts. And we found that with P equal to 0.3 and Q equal to 0.7, we got like a better energy, better result. Even though the results seem to be similar, but when you can see here, the network lifetime here ends at almost 6.5 rounds, while with this parameter, it's almost 8.5 rounds. That's better actually. So the protocol was actually proposed was actually compared to Leech and Pegasi. You can see that even the time until the first node dies was extremely extended. This is actually almost the time till all the nodes dies with Leech. So the protocol really outperformed Leech and Pegasi in terms of energy consumption. As you can see here, the energy consumed here by the proposed protocol was a little bit higher because of the learning process. But after the learning process, the energy was really optimized, was really minimized. As you can see here, this is the average energy per round for each node. So as a conclusion, we proposed actually energy balancing routing protocol, which is a flat-based protocol for wireless sensor networks. It is based on reinforcement learning, and the implementation is done into 2 phases, and it achieved a very good performance in terms of energy consumption and network lifetime. And it outperformed Leech and Pegasi in terms of these two metrics. So the future work will be extending this to a cluster-based routing protocol with more considerations, such as heterogeneity of nodes and scalability and QoS. I would like also to add some QoS parameters such as end-to-end delay or delivery ratio and so on. So we would like to extend this to make it more complex and try to test it with other protocols also to see how it will perform. So this is the end of this presentation. I would like to thank you very much for your attention, and any question, suggestion, or recommendation are really welcome. Thank you very much.